So the first thing I want to do is go through all of these and underline if they're a compound. And so to do that, let's stop and think, what is a compound? How would I recognize a compound? More than one capital, no charge showing. Compound, compound, compound. Ooh, that's an element, chlorine. And this is an element because there's only one capital. This is an ion because even though there's more than one capital, there is a charge showing. Compound, 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 ion, element. Okay, the next instruction said that you're gonna, or one of the instructions said that you're gonna circle if it's covalent. So there's two kinds of compounds, ionic and covalent.
Is that what, I'm sorry to interrupt you, but it says molecular in nature. Is that what covalent means?
It is what it means.
Okay.
Yeah. So molecular in nature means covalent. And there's two kinds of things that can be covalent. But covalent just means sharing electrons. And so we can have molecules, covalent compounds, or molecular ions, which are polyatomic ions. And so here I have an ion, permanganate. It is molecular in nature. I know that's weird, but as soon as I see that it is a polyatomic ion, that means it is molecular in nature. And nature doesn't mean as we find it out in the real world. Nature means in the way that it exists. It's nature. And covalent simply means sharing electrons. So if something is sharing electrons, it's covalent, it is molecular in nature. What kind of things are molecular in the way that they are? Polyatomic ions, elements, and then molecules. So there are three categories of ways things can be molecular in nature. How do we know that these are all molecular in nature? So the permanganate is not a great example. I'm going to erase it right now. Let me pick something that is more obviously molecular in nature. We know that it is covalent or molecular in the way that it is, even if it's an ion, because it's on metals only, or at least it's not metals. So even something like boron trifluoride, which has a metalloid, and a nonmetal, is molecular in nature. Okay, so this here, trichloride. And the reason I said trichloride is because we're naming a covalent species. So in order to name this, we had already classified it. This next one is aluminum chloride. Why did I not say aluminum trichloride? Because it's ionic. Why is it ionic? Because it begins with a metal. So this is covalent, and this is ionic. And for things that are ionic, we use the expression formula unit, the unit that represents, the formula that represents the unit that is repeating in a three-dimensional way throughout this crystal lattice. That is the long-term repeating order of things that are ionic solids. Okay, so now we have one that has Si, silicon. So we look to the element on the left to decide, are you a nonmetal, a metal, or a metalloid? For the metalloid, it behaves as a covalent species, just like boron trifluoride. So for this one, I don't say silicon 4-chloride. That would be an ionic name. I say silicon tetrachloride because it's sharing electrons. Metalloids behave as nonmetals. Okay, so the next one.
Shouldn't we put a circle around silicon tetrachloride?
Oh, yes, we should.
Okay.
Thank you. The next one is an element, but elements can be molecular. How many molecular elements do you know? So phosphorus, poor old Superman, there are 3 polyatomic elements. And there's 7 diatomic elements, and those are all covalent. So there's 10 elements that exist in a covalent way in our class. So I'm going to circle that because it's not a compound. I didn't underline it, but it is an element that is covalent. Well, how's it covalent? There's more than one. So now we're looking at chlorites. We didn't underline it because it's not a compound, because there's a charge showing. Should we circle it or should we box it?
No boxing.
No boxing. But we can circle it. It is molecular in nature. How do we know it's molecular in nature? Because it is a polyatomic ion. And there's only nonmetals present that have gained an extra electron. Okay, ammonium chloride is tricky, and this is why. Oh, let me name these things. Chlorine, chlorite. At this moment, a few of you may be thinking, and if you are, it's totally fine because this is appropriate at this point in the semester. Why is that not dichlorine? Why is that not dichloride? And the answer is because it's an element. Just call it what it is. It's chlorine. Okay, this next one, ammonium chloride. Ammonium is a covalent species because it is a polyatomic ion. So circle that. But it's a cation, and when it's with chloride, that's an ionic compound. So put a box around it. So this one gets all 3 because it's an ionic compound that contains a polyatomic ion. I'm going to say that again. Ammonium chloride is an ionic compound that contains a polyatomic ion. There's a lot of things going on there. Okay, sodium sulfite. What do you think? Box, circle, both, neither?
Box, I think.
It is ionic. It begins with sodium, and sodium is a metal. Yep. Is a polyatomic ion present?
Perhaps.
Ammonium sulfite?
Yes.
Yeah. Okay, carbon dioxide. Box, circle, both, neither.
Box?
Is it ionic? Is carbon
Oh.
metal? No, circle.
Circle.
But thank you for playing. Potassium chloride.
Box.
Dichlorine monoxide.
Circle.
Chloride.
Circle.
Neither. If there are no subscripts, it can't be covalent.
Okay. Okay. Okay.
Iron. Neither. Okay. So I'm going to show you what I see that is wrong, and then I'm going to show you why we understand how to make it right. I'm going to erase this page. Nope. Let me just slide over. Okay, so sometimes, and this is a question that I ask on quizzes and tests, I'll say, and I will always use the same things. Underline for compound, circle for covalent, box for ionic. I will always pick that way of identifying things. And then I will put this on a quiz or a test. And students know it's a compound. And they know it's ionic because this is iron 2 chloride. And this is where they make their mistake. They go, oh, that's chlorine. But it's not. It's not chlorine. When we were given the instructions, you know, here is a name, write the compound, the formula for the compound. This is what we thought 2 weeks ago. Iron 2 is a metal with a +2 charge. Chloride is a halogen, so it gains 1 electron to become chloride. It's a halide. I'm going to need 2 chlorides to balance that +2 charge on iron 2. And then we stuck those 3 ions together and came up with the correct formula, iron 2 chloride. But sometimes, because this week I've really been hammering, you know, you got to know your diatomic elements. When you take the practice quiz or the quiz, hopefully you learned it on the practice quiz, that there are 7 diatomics and 3 polyatomics, and that you have to remember that the molar mass changes because of that. So I'm hammering the idea of horses need oats for clear brown eyes over and over again. That sometimes people will see this and go, oh, that's chlorine. But does it make sense that iron 2, which is a cation, would be attracted to a neutral molecule? No, opposites attract. Cations stick next to anions like little tiny magnets. So no, this is, that circle does not belong there. So that's a mistake students make because the ideas are still a little bit jumbly. It's like wet cement in our brain. We haven't cemented things. And when we do cement them, we want to cement them correctly. And the question might be, well, you know, that's a lot of details. Does that really matter? Is that important? And the answer is yes, it's important. So I want to show you the why. In 2 weeks, we're going to be looking at, we have some things that react. And so I might have a species and I have to decide in water, does this dissolve? And if it dissolves, does it dissociate? So we're going to talk about something called solubility, which is when I put this in water, can I still see it? And if I can't, it was soluble, it dissolved. Did it dissolve? Because if it dissolves, I can't see it anymore. So think of things in your everyday life like sugar and salt. You put them in water and you give it time and stir, you can't see them, it just looks like water. You know, but if you want to play a prank on somebody and you put salt in their water and then they drink it, you know, they didn't expect salt or sugar. Like salt water or sugar water or pure water, you know, it just looks like water. Why? Because the solute, either salt or sugar, dissolved in the solvent, and then we couldn't see them anymore. Now, when covalent things like sugar dissolve in water, covalent things are sharing electrons and they stick together. And the smallest molecule doesn't change. It's just now it's aqueous. So what was maybe a solid, sugar from my sugar jar, is now dissolved in water and I can't see it and it tastes different and that can be alarming. But the smallest unit, which is covalent, is still the same smallest unit because that's how covalent things behave. Covalent species may dissolve. I can't see them anymore. But the smallest unit is retained. If something is ionic, like sodium chloride, I really wouldn't want to be surprised by sodium chloride in water. Things that are ionic, if they dissolve, they dissociate. They break into the ions that they're made of. Ionic species if they dissolve, I can't see it anymore. And I know it's in there because I put it in there, or I know it's in there because I can taste it's in there. If they dissolve, they dissociate. And dissociate is a fancy word for they break into ions. Dissociate. The ions that they're made of. And so we're going to need in 2 weeks to look at something like this, which is iron 2 chloride. It's ionic. And know that chlorides are generally soluble. There's only 3 that aren't. It's going to break into the ions that it's made of. It's going to break into iron 2 and 2 chlorides is the correct way of writing that. A wrong way of writing that would be to say iron 2 chloride, a soluble salt, ionic species are called salts. A soluble salt breaks into iron 2 and chlorine. That would be not true. That'd be wrong. So the exercise that I gave you today is a chance to basically look at things you've learned to name and then classify them in your brain as to compound, yes or no. And if it's compound, ionic or covalent. And even if it's an ionic compound, it might have a covalent part that is going to stick together when it dissolves in water. So what I'm preparing you for is when we take the nomenclature we've learned and we work backwards to break things in water as appropriate. I don't know what happened. I don't know. I was running low on electrons, my computer. Maybe that had something to do with it. Okay, so I think I already said the part about do the work, compare with friends before you turn things in, and don't Google that.
And happen again. All right, now you're good.
Okay.
Whatever that sentence, maybe we should just skip that sentence.
About cheating?
No.
Okay, I'm going to skip the sentence this time. Okay, so I was asking you, would you prefer that I just made a key or that I went over the second page tomorrow? How about I make a key and I post it, and then tomorrow, if people have questions, they can ask.
Okay. Yeah, I didn't want to speak for everybody. A key works for me, but I don't mind
Key
you going
works for
over it
me.
again.
I feel like that would work for me as well.
Okay, I'll do that. I will make the note to self.